Ooh, alright, let's make this a little bit bigger on the screen. Alright, up to now, what we've been doing, I'll just scroll back through this work and then we'll quickly come back to finish off what we're doing in this lab. So we've done a lot of practice with series RC circuits, and we've certainly gone through the theory over and over and over again. And then towards the end of that particular lesson, we went through some parallel RC circuits as well. As you can see here, where we're working with currents with the same voltage across each component, we're playing with different currents. But in today's review of RC circuits, we're working with the series RC circuit again in this lab, which we're revisiting because I wasn't quite happy with how it went the first time. We had a 1K resistor with 1 microfarad, and I'll just complete the other details here. We had 900 Hertz, and I did ask for 4 volts peak to peak, but when I take a closer look at this diagram that I've got on the page here, I can see that the input channel 1 is set to 500 millivolts per division, and that would be this yellowy coloured trace, and I've got the sine wave negative peak at the bottom of the screen, but the positive peak, ooh, look at that. Look, I'm not going to call it a fail, it's just a case of maybe not being quite accurate and observing what was asked for there. So I'm going to call that, okay, I'm going to call this 7.8 divisions at 0.5 volts per division to give me 3.9 volts peak to peak. And then when we run the maths on that 3.9 volts peak to peak, because I did want that voltage in RMS, I'm going to have to divide the 3.9 volts by 2 and then multiply it by 0.707, and that gave me 1380 millivolts. 1380 millivolts RMS. And look, I'm not sure, I think on the board I might have put up 1370 millivolts in one of the parts of this lesson topic, but you get the idea. You've got to be a little bit accurate here, especially when it comes to the calculations. Otherwise, when you go into a calculation from one end and then you try and reverse engineer it and come in from the other end, you're going to have an imbalance in your answers because you've used different quantities along the way. So I'll make a note then that we have got 1380 millivolts, whoops, RMS there. Alright, what's one of the first things that we have to look at here? When we left the previous section of video, we were looking at this time difference between the two sine waves, and we did say, and I'll repeat it here, it's very important when you do this to have both of the waveforms lined up the way I'm doing it over the center axis of the graph, or the set of graticules on the screen. And we've measured it using the cursors, and we come down to 256 microseconds. And at 256 microseconds, we have to make into an angular difference out of 360 degrees, so 256 microseconds. And if you remember, I'll just come down here to plot this, 1 divided by 900 Hertz was equal to 1.111 milliseconds, and that's going to equate to 1111 microseconds. So as a ratio then, the period at 900 Hertz 1111 microseconds, and the difference that we've got here is 256 microseconds. And of course we're after a angle, so we multiply it by 360 degrees, and we get 82.95 degrees. Look, I'll write it down as that, and there's a reason for doing so. 82.95 degrees. I mean, any other time I would have called that 83 degrees, but in fact I'm a little bit suspicious about this 2.95 degree part here anyway. I think it should be more like 80 degrees. I'm not sure why. Maybe if we had a closer look there, it certainly appears to be 256 microseconds, but as you'll see from the board work, when we come in the other way, it would have appeared to be more like 80 degrees instead of 82.95 or 83 degrees. Some other things that we can do with this diagram while I've got it open on the page here would be to work out the impedance. Any of these circuits, series RC circuits, once you've got a frequency, one of the first things to do is to work out the impedance. We'd better go ahead and write that 900 Hertz up there just to complete that. We've got our 1 microfarad, so the XC, first of all we need to find out. XC equals 1 on omega C, which is 1 on 2 pi FC, which when we break that down, be 1 on 6.28 times 900 times 1e minus 6. And that worked out to 177 ohms. 177 ohms XC. I'll write that up here. 177 ohms for XC. And then the impedance in this circuit is going to be equal to the square root of R squared plus XC squared. And if you want to go about it using Pythagoras, that's what you do, but if you get a little bit smarter, of course, as I've shown in other videos, you'd use your calculator and use the rectangular to polar function on the calculator. Always put in the resistance first. In this case, so it'd be on my FX991, it'd be shift pole 1000, comma, and then the XC to be 177 equals, and of course I get the resultant of 1015. Not sure if you can see that in the calculator there. I'll write these down. 1015 ohms is the impedance, and the beauty of doing it on the calculator using the rectangular to polar function is that I also get the phase angle in the circuit at the same time, theta, which is showing me 10 degrees, 10.03 degrees, so 10 degrees. And this is what I was saying a little while ago about the fact that using some measured values and using this 256 microseconds and looking at the angular difference, I got for the other side of theta, which is theta 1, I got 82.95 or 83 degrees, and yet using the impedance with the polar function, I'm getting the phase angle at 10 degrees. So I'm a little bit suspicious about that 83 degrees. It just does not seem to stack up in the circuit. I might just make a note here that I put in using the polar function on my calculator. So pole, and that'd be R, comma, XC. And that gave me both things. So that 10 degrees there is actually theta, the phase angle of the circuit. Alright, so other things that we can work out with this, we do not know the size of VR at the moment. Now, we can rearrange the circuit, which we certainly going to do in class. To rearrange that circuit, we'd have to put the capacitor at the top, and we'd have to put the resistor in shunt with the output, and then this would be a leading circuit. And there's our same frequency, of course, everything being the same, 900 Hertz at whatever voltage we had there before. And if I did that with the oscilloscope connected across the resistor, that would give me, of course, VR. Now, we have not gone ahead and done that yet, and I have to think, if I'm going to construct a phasor diagram for this, I really need to know, if I do it with voltages, I really need to know the voltage of the resistor in this circuit. And I've got a few different ways I could do this, because I now know the phase angle of the circuit, which is the difference between the supply voltage and the circuit current, and that'll be a negative phase angle because it's a lagging circuit with capacitor in it. And look, while I'm here, I just scroll up on here again, I'll put the head channel 2 of the oscilloscope there, channel 2. And this is a lagging circuit. Write that in red, it's quite important, lagging. Lagging, because the output is taken across the capacitor, and the voltage across the capacitor is lagging the circuit current by 90 degrees. So hence that's called a lagging circuit. It's lagging the supply voltage by angle theta 1, and it's lagging the circuit current by 90 degrees. So what I was saying is, how can we go ahead and find out VR? We know VC, we know angle theta, we know the supply voltage. A few different ways that we could go about doing this again. I'll just put a little inset box here on the page. Ooh, that's a bit messy, isn't it? Pretty crook when you can't draw a straight line. Okay, I'll just cheat here and use that function, drawing package. There we go. And we know then that the supply voltage, Vs squared, is going to be equal to VR squared plus VC squared. So then we should just be able to rearrange that equation and say VR squared will be equal to Vs squared minus Vc squared. Simplifying that, of course, we can get rid of the square from VR, and that'll become VR equals the square root of Vs squared minus Vc squared. And if we plug some values into that, what did we have? 1380 squared minus the 230, and they are in millivolts, of course, all in millivolts squared. Okay, so we run the maths on that. Square root of 1380 squared minus 230 squared, and we come up with 1361 millivolts. And we go ahead, we can construct the phasor diagram for that now. This is VR, of course. VR. So on our graph, we can label that. VR, I've already drawn it, 1361 millivolts RMS, and VC, remember what VC was? 230 millivolts, and we can construct a bit of a parallelogram with our phasor diagram, and then I'll use a different colour for the resultant. There's the resultant to our phasor diagram, and that resultant of course represents VS, and VS we had mapped out before at 1380 millivolts RMS. I'll use the same colour, 1380 millivolts RMS. It's all in RMS, of course. And that's looking pretty good. The hypotenuse in our little triangle here is 1380, that's the largest side. And then if we're considering this angle here, which is theta, and we already knew that that was 10 degrees, we mapped that out before, we've got the adjacent side, which is 1361. We've got the opposite side there, which is going to be 230, isn't it, if you think about it? Because, maybe I'll do that in red. That side there is the same size as this side, so that VC, 230 millivolts, this is VC down here, and that is 230 millivolts. So again, we could do some trigonometry on that. We could take the tangent of that angle there, and we could work in conjunction with the opposite side, which is 230 millivolts, and the adjacent side, which is 1361. But we already know what the angle is. However, we'll go ahead and we'll do that anyway. Just see what we work that out as, because that 230 millivolts, that was a measured value. I'll just write that down here. That was measured, not calculated. And if that was out by just a little bit, that will throw our calculation out. So 230 millivolts. So we've got the tan theta equals opposite on adjacent. In this case, it's going to be equal to VC divided by VR. So therefore theta will be equal to inverse tan of VC on VR, and VC on VR, of course, is down here, 230 divided by 1361. Now, interesting here, I've got a calculated value and I've got a measured value here. However, that calculated value was derived from, oh no it wasn't, yes it was derived from that measured value, so things should stack up here. Let's see how we go. So, right, so we've done that calculation, inverse tan of 230 divided by 1361, and just as we would have expected, we come up with, well, very close to 10 degrees, 9.6 degrees. 9.6 degrees. We did say 10 degrees, we've got 9.6 degrees. A little tiny bit different there, but really not too much to worry about. I might just put a circle around that in grey and put a circle around that in grey, and then we can say, well, on the day, you know, I'd be pretty happy with that. So just to review what we've done then, I'll scroll back up here. We had the reference circuit with the 1K ohm series resistor and the shunt capacitor, 1 microfarad, 900 hertz coming in at around about 4 volts peak to peak, give or take. We did say that there was a little bit of measurement error there, we can see on the oscilloscope. And we worked out we used the oscilloscope to measure the time difference between the two waveforms, and then we put that into an angular difference. We did measure 83 degrees, and that's a bit of a worry because after we've gone through and done the rest of the maths on this circuit, we've worked out the reactance, we've worked out the impedance. We could have done an impedance phaser as well, and I think we would have still found out that we had our 10 degrees, because there it is showing there, 10 degrees. So 10 degrees, we needed 80 degrees to make that 90 degrees all up, and that 83 degrees just doesn't seem to stack up. So not sure why we've measured that. Probably what I would do in the future would be to, and I've done this in other videos, expand the waveform out on the oscilloscope to get a much more accurate reading, because you've only got to be out by a little bit. I mean, 3 degrees in 90 degrees is not a big percentage error. And then we've taken the VC and the VS to work out VR, and of course we could have also measured VR, and we'll do this in the second part of the lab. We'll change the circuit around to put the resistor in shunt and make a leading circuit with the capacitor in series. But in absence of doing that yet, we've been able to use Pythagoras and work out what VR is, and then we've constructed our first phasor diagram using VR, VC, the resultant VS, and we've got the phase angle in the circuit, which is 10 degrees. And I might, just before I wrap this up, draw in, also in that same colour, theta 1. Theta 1, which by all accounts here measures 80 degrees. 80 degrees plus 10 degrees to give us our 90 degrees in that phasor diagram. Following this, there's a video which covers the board work for pretty well the same thing, but maybe with some slightly different explanations. And I think in the board work I do things a little bit different to work out the phase angle of the circuit.